Hello everyone, welcome to Mechanics-V18. So in the video series of previous year question of CSIR-UGC, we have already solved 6 topics, and currently we are in the 7th topic, which is Schrödinger equation, and we have solved 5 questions from this topic. So let's move to the 6th question, and the question is, this question was asked in July 2024. So the question is, a particle of energy E is scattered of a one-dimensional potential which is given by lambda delta x. So here we have given is lambda delta x. This is a delta Dirac delta potential, where lambda is a real positive constant. So this value lambda is a real positive constant. Okay, with transmission amplitude t plus. So the transmission and reflection, these we have to find the amplitude of how much when wave interact with the potential, and how much the wave get transmitted and how much the wave get reflected. So the transmission amplitude and reflection amplitude is given by T and R, and here T plus is the transmission amplitude. In a different experiment, the same particle is scattered off another one-dimensional potential minus lambda delta x with transmission amplitude T minus. So for the one-dimensional potential lambda delta x, the transmission amplitude will be T plus, and for the one-dimensional potential which is minus lambda delta x, both are the delta function. So for this, the transmission amplitude is T minus. So in the limit of E tends to 0, when E becomes 0 or nearly 0, the phase difference between T plus and T minus is. So what will be the phase difference? So for this, we can derive the transmission amplitude and then find the difference between their phases. So derivation is a bit lengthy, and if you want me to derive that, you can comment it and I will derive in the next video. So just we will move to the transmission amplitude. How can we calculate it? By using its formula. So the general formulation of the transmission amplitude for a free particle, we can say, for a delta when it is scattered through a delta potential. So the solution will be, so the transmission amplitude T plus minus is equal to, what we can write is K by K plus minus I m lambda by h cut square. Okay, so what is K here? K is K can be related with energy, which is we can write it as E is equal to h cut square K square by twice m, which is energy of a free particle. Okay, so what here limit is, if E tends to 0, it means when E tends to 0, here K should be tends to 0 in the limiting value, K tends to 0. Okay, so let's go for the positive delta, which is T plus when scattered from lambda delta x. So for this is for K plus I m lambda upon h cut square. Okay, so when K is equal to K tends to 0, then this part is going to be very small. Okay, so we can directly write it as for K tends to 0, K tends to 0, this goes to K by I m lambda upon h cut square, which is h cut square K by I m lambda, and we can write it as minus I h cut square K by m lambda. So we can find the argument for this transmission amplitude, which could be, we can say here, this is the complex part. So x plus I y. Okay, so the argument will be tan inverse y by x. So from there we can find that here it is minus y. This will lie on y axis. So either pi by 2 will be 0 and minus pi by 2 will be for minus pi by 2, this part will exist. Why complex part will exist. So here we can see that for minus I, it will be minus pi by 2. Okay. This is just, you can calculate it, but this is just from the plot, we can directly say it. So the argument will be for theta is minus pi by 2 for this, which is phase. And again for t plus, we can go and we can simply see here that it will be I h hat square k by m lambda. Just solve it by this, as similarly as we have solved here. So now here the argument will be pi by 2. So the phase difference will be t minus argument minus argument t plus is pi by 2 minus pi by 2 is equal to pi. So let's look at the solution. What we have here, option B is the solution, where B is pi. Okay. So thank you. So only one question is left in this part, so we will solve it in the next video. Okay. Thank you.